seminar. It's my pleasure to introduce Bolan Zhu, who's joining us from Columbia University, where he's an assistant professor. So Bolan did his undergrad partially here. This is the University of Michigan program that used to exist. And then he went to Zurich, then the University of Washington, where he did his PhD.
Yeah. Thanks, Johanna, for the intro. Yeah, so I think it's the first time I'm actually back after I graduated in 2011. So it's been 14 years, but I was, I've been to quite a few schools, quite a few places, but I along the way I was really grateful about the kind of education I received from here. So that was really helped me to win a long way. So yeah, very happy to be back. Okay. So today I'm gonna talk about some of my group's research focusing on energy storage, especially about how to participate in the electricity market and how do we help their participation. So first, let's get the obvious out of the way. This is what we are talking about. So these are by meaning energy storage in the power system. We are mostly referring to these giant batteries. That now are in gray, and they come, basically they come like this. If you look at the actual thing, this basically giant, looks like shipping containers with air conditioner, and I guess we don't see them every day, but they are making these batteries are making a huge impact to our power system, also our daily life a lot. So so if you see here on this figure, this shows kind of the US distribution of electricity market. In the United States, we have 7 deregulated electricity markets. So in this colored area, obviously this is Michigan, which is part of the MISO territory. In the power system, electricity has to be balanced, supply demand to be balanced through a market framework. Okay, and on the other hand, here, this shows kind of the rise of battery capacity in the United States. You see here, we basically go from before 2020, so about 5 years ago, we have nearly zero. That should be like less than 1 gigawatt hour of these giant batteries, and they are basically all lithium-ion batteries on the grid. Until now, we are also surpassed 100 and heading towards 120 and even more in the United States. So there's a significant development over the past 5 years, especially look at the distribution. These are basically led by California and Texas. Okay, so if you wonder what our batteries are actually doing, they are basically in the market, they arbitrage, but what they actually achieve is it help to mitigate the supply-demand imbalances. So this is one of the articles from New York Times showing in 2021. This is one example from California, right? I guess some of you may heard of this, like a dog curve that has, plenty of solar generation during the day, but then during the late afternoon or early evening, the sun goes down, and that creates a huge problem that we need to ramp up all the generator to meet this change. So now batteries are helping us to achieve that. So you see, will be the most of the time that a battery got discharged, and it doesn't show you that most of the battery do charge during the day. And this is also not only good for grid, but also good for sustainability, because it's basically battery are charging from clean solar energy that otherwise will probably get wasted. Okay. So now this is actually one of the newest figures, I think published earlier this month by Financial Times. I call the sources for model energy. It showed that in California, battery have reached 25% of the peak load, right? And here the peak load are really the yearly peak load. So if you think about on a daily basis, battery are making like the power of the battery are reaching like 30, 40, even 50% of the daily demand. Of course, it's power, not energy. And followed by Texas, and also shows UK and Australia. And we went a kind of a long way, not really a long way from here. So we, if you look at history, back in 2010, this is where we talk about battery, how do we use battery in the power system. And I think the first structure application was frequency regulation. In that case, battery frequently charge and discharge. And you can see this is a very good application. It has higher power requirement, but low energy requirement. At that time, battery are around 10 times the price that they are now, right? So they're all very small and 15 minutes batteries. And then in 2015, 2020, the battery started to provide other ancillary services, more like a reserve and a ramp. And the battery kind of reaches around a 1 hour duration. And starting from 2020, the battery are mostly doing energy arbitrage. That's the main service in the power system. It's a no-brainer. You have so many batteries, and the ancillary service is just a small portion of the electricity market. So if you think about battery reaching 25% of the California peak demand, so you have to participate in the energy market. And also the battery duration have increased from 2 hour to 4 hour duration. And a lot of projections showing by 2030, we are heading towards 100 gigawatt of batteries in the power system. Okay, so what's the issue here? Why are we doing this research? It kind of goes back to the fundamental concept of kind of electricity market, which is kind of one of the key ideas in one of the first book in this area, Spot Pricing of Electricity, I believe published maybe 30, 40 years ago. It's really, of course, this book was mostly written about conventional thermal generator, natural gas, fossil fuel. It's that in a competitive exchange market, based on resources should converge to the physical marginal cost. And that's how we used to evaluate efficiency of the market, which means, that also means the market helps to find the optimal allocation of resources, right? And for thermal generators, fuel prices should serve as a baseline for Bay design and the market power monitoring. That means that if you are a fuel generator, natural gas generator, you are in a well-designed and efficient market. The bid submitted by this fuel generator are basically translated from their fuel cost, right? And this is kind of the fundamental idea with market design. But on the other hand, how about storage? And it turns out that we don't have a very good understanding, or we are having improving our understanding on this perspective. So this is really what my talk will be about in today is from a two perspective. First, we look at this problem more from a market mechanism system operator's perspective. Is given that we are not going to change our market design anytime soon, and we already have so many batteries on the grid, how to understand this battery, how do they behave in the market? And is market still efficient? Are we still heading towards the right direction with so many batteries? And of course, the answer is roughly yes. I'll talk about why. But then, given that, how do we improve the storage market participation? Of course, this is more from a system from a storage perspective, that how do we improve their market participation strategies in the power system? Okay, so in the first work, I want to talk about how we understand equilibrium of strategic storage in the electricity markets. It's really a more tailored study towards the US market design. So for those who studied power system, every place the electricity market design is slightly different, especially if you compare Europe with United States. United States, we have a very structured two-stage market clearing. We have a day-ahead market, which essentially is a forward market. Everything is cleared based on forecast. It's not just any forward market. This is really goes back to in the old days, how do we schedule thermal generators? We need a unit commitment here. But this is basically in our study, this is a day-ahead market, and also real-time market that settles things based on realized demand, and the demand must equal to supply at all times. Okay. So given this kind of a two-stage market clearing, so Jerry, who is the lead author in this work, who used to be a business school student at Columbia, developed this kind of two-stage, two-period framework. So in both markets, we had considered a peak demand stage and off-peak demand stage. And you really think about a day, we can also always decompose a day into like like a peak demand period and off peak demand period, right? So in the day-ahead market, we clear everything based on the expectation of the demand, and then in real-time market, we clear the realized demand, and these are model has joint normal distributions. And then we also have battery decisions that in the day-ahead market and also in real-time market, but the internal market is physically binding, so they become the kind of function of the realized demand. Okay, and we have our in our simplified 2 time period model, with Z positive value represent charge discharge, and also we have our simplified 2 period SOC constraints in the sum of charge discharge equal to 0. Okay, so this is our kind of a decision and uncertainty space. Then we introduce our supply curve or supply demand balance. We introduce the cost function or the supply function GS, and here we divide them into slow generators and fast generator. And the idea is slow generator represents a generator that can only be scheduled in their head, while fast generator the one that can reschedule in real-time market, right? And also then in both day ahead and real time, we have a demand balance minus the storage decision here. Okay. Yeah. And then we also introduce KF to be the share of fast generator, then we can write out the share and of the supply curve, and also derive analytically the price sensitivity function based on the demand and based on the storage, right? So this is kind of the framework we or more specific Jerry came up with, and based on the framework, you know, it's go on. Jerry proved many different characteristics of this framework. So I want to highlight 2 interesting findings. One is understanding the withholding behavior of strategic storage. In this case, if we compare, you know, this is the storage discharge decision in day-ahead market and in the real-time market, and in the up, it is the centralized case where we maximize social welfare, right? This is kind of the ideal outcome that kind of minimize the cost of electricity, where below is the case from a market participating storage. And we show that here with the market outcome, storage will withhold capacity compared to the day-ahead one, right? And another thing is we look at both of these cases, you notice, right? In the storage discharge decision, it depends both on peak demand and off-peak demand. So the storage discharge decision is never decided only on one time period. It's on both multiple time period. And this also fits our intuition that if you're storage, you are arbitraging price differences. You know, just like people trading stock, you will not only look at when you buy the stock, but you also will think about when would I sell the stock in the future, right? So this also shows that being a battery, the decision has a speculative nature, even in the vertically integrated case. Okay, and that will be one of the major difference compared to thermal generator, which should only consider their fuel cost. But here we show the battery has a nature of being a speculative player in the market, right? The other thing we look at is, of course, market efficiency. In this case, we introduce this concept of price of anarchy, which basically, I think is a more widely used concept in business school of describing market efficiency. It basically shows the ratio of cost reduction from a no battery baseline case versus a system with battery. And this one is a vertically integrated battery, which is kind of a welfare maximum case. The other is a market case. Okay, so if POA equals to 1, that means the market is efficient. But if the greater the POA, it means the market is further away from being efficient, right? So on one major thing shows in this study is we show that POA is bounded by the number of battery, right? So which means that with more batteries participating in the market, we do have a convergence that the market will converge towards POA close to 1. Okay, and also the speed of convergence is faster than a linear rate. Okay, and also we show that POA will decrease with higher share of fast generator, which makes sense that battery are basically paid for being fast. So if you have other fast generator in the grid, there are more competitions, so the market can end up being more efficient. Okay. So based on this, we can kind of summarize the key takeaways. Is the battery have to be strategic. Okay, it has to think about what happens in the future, right? In both the market case and the centralized case, right? But which means that current market design doesn't really offer storage an option to being honest bidder, right? There's so by honest bidder, meaning the battery cannot just submit its physical parameter to participate. However, we do show the competition still helps with the current market design. That's with more competition, we will converge to social, to the welfare efficiency. And also then it's important that if we can derive better participation strategies for batteries, of course, without trying to exercise market power, then it will be a beneficial improvement both for the batteries. It may get be more competitive and more profit, and also good for the overall system performance, right? So, you know, based on this result, we now want to look at and how do we help battery to do better in the market. So the first thing or the first work I want to talk about in this direction is how do we come up with better price prediction for energy storage, as we mentioned, the energy storage have to be speculative. If you participate, this is just like trading stocks. You always want to predict the future, right? So this is also, as mentioned, current market is not a true spot market, meaning there's no way for the battery just to participate in the market by emitting physical parameters. And this is also recognized by a few papers from other colleagues working in this area. And then the storage must leverage base to indirectly manage the state of charge and the degradation opportunity cost. And this is a non-trivial problem. A company like Fluence, you know, which is a joint venture between Siemens and AES, which one of the storage developers, literally acknowledges this in their website, saying they're basically saying the traditional bidding mechanism does not work with energy storage. We use state-of-the-art machine learning to AI-powered bidding software to help your battery to bid into the market. So if you wonder what they are doing, of course, we don't know exactly what they're doing, but we kind of will show you kind of some idea about how we may use machine learning to help storage to address this issue. Okay, so first, let's look at kind of the minimalist formulation of a battery arbitrage problem. Of course, this is the deterministic version, and it's pretty simple, actually. So the key here is given the price lambda. So lambda is the price of electricity, and the P represents the power, right? And of course, we have two variables, one for charge, one for discharge. And the reason is we want to, and there is some efficiency loss here that whether you charge or discharge, the battery will lose some energy. And so that's the energy balance constraint. We also have energy capacity limits, the power limits, and also one of the condition, you know, or one of the sufficient condition I often use in our lab is to show, to enforce, because this is the arbitrage problem, that the battery do not discharge when the price is negative. And that's kind of just avoiding a nuanced situation where battery may charge or discharge at the same time, okay? However, the main challenge in this problem is lambda is uncertain. Also non-stationary because the market situation changes all the time, and it doesn't really have a very good analytical expression of distribution. Okay, and also there's a very tight upper lower energy limit, which also adds some complexity to control, and then also some learning problems. Okay, so if you wonder what the price will actually looks like, this is one example from New York City. And this is actually not a very particular day. You know, it look at here. This is May 2019. Okay, and you know, May is in the spring. That means the demand is not too high or not too low, right? It's a very mild season, but still we see some price behavior looks like this. And this is from New York City, so this is likely caused by some congestion between Manhattan to upstate New York and also to Long Island, right? But this is also quite typical. And so we mean by the price is very volatile, very stochastic. This is what we mean, okay? The price will exist. And this is basically a 3-day worth of prices, okay? So, and this is basically what we want to predict, okay? So how do we solve this problem in general? So there are many kind of, if you look at method people propose, they kind of fall into one of these categories. The most common way is model predictive control, MPC, which we predict the prices and run optimization. Okay, and this is also the most favored method by our industry colleagues. And the advantage is really this is a very intuitive and modularizable solution, right? You can completely decouple your price prediction model with your storage optimization model. Especially if you think about the industry, you may get your prediction actually from third-party providers, right? But the limitation is it does require accurate price forecast, and the base generation can be non-trivial. We'll talk about that later. Another way is reinforcement learning, that we learn the policy through interactions. The benefit here is data-driven and flexible, but one limitation here is encoding capacity or degradation or externality into reinforcement learning can be challenging. I will say can be time consuming. It stays doable. It just depending on how much computation resources you want to spend on doing price arbitrage. Another thing that in our industry colleagues really have a problem is the interpretability. That's kind of also a common issue with reinforcement learning, that they want to make sure they understand what the model tells them. Okay, and the third way is stochastic dynamic programming, or dynamic programming in general. It's a classical and it's kind of a fundamentalist approach, theoretically rigorous, but the limitation has been it's computation intensive and difficult to adapt also to external factors. Okay. So in our case, actually, the final solution we propose is kind of a combination of MPC and more dynamic programming here. So in the first work, it's mostly about how do we came up with price prediction. And the second work will be how do we use dynamic programming to generate bids for storage. Okay, so price prediction, given the volatility we've shown so far, has been a bit challenging, especially if you think about if you're using neural network to predict prices. The neural network tends to overly smooth things. It minimizes a norm to error. Okay, but if are a storage, the battery is arbitrage price differences by nature. So a battery is less interested in the average trend of price, but it's more interested in the timing of price spikes and the valleys, right? So if you look at it here, of course, this is not the best example that we can do, but this is basically just using some off-the-shelf LSTM network to predict the price of electricity 5 hours ahead. You see, actually, the general trend of LSTM is not so bad, but if you look at the actual timing of the spike and the valleys, is not really matching the actual prices. Okay, so To solve this problem, we introduced this concept of decision-focused learning. So here, this shows a typical MPC pipeline, right? We have our prediction features. We feed them into our price prediction. Then we feed the price prediction into the optimization model. We get the solution, we get a profit, right? So then the idea with decision-focused learning is we just loop back our final objective into the training of our prediction model, in this case, likely a neural network, right? And this concept was really one of the representative work describing this concept is the smart predict and optimize, or called the SPOO framework, that kind of define the training regret loss function based on this framework. So the key here in training this is to derive the back propagation gradient that if you want to minimize or max, sorry, I think this should be minimized. You want to minimize the regret given the price prediction, given our final objective. You see here, P will be the decision variable, but W here, or the weights, will be the final parameter you want to train in the neural network. So the key here is you want to get the gradient from the P, between the P to the weight of the learning model. So, and then we can derive this using the chain rule here, where the partial derivative between the price prediction to the weight of the neural network, that is come handy in the machine learning packages. But the real key in our case is to derive the gradient of the optimized battery decision to the price prediction. Okay, so so this framework is decision-focused learning, and in the literature, there are many different approaches in solving this issue. And the fundamental challenge here being that our model is very linear, right? If you do a derivative of the linear function, it lost the smoothness. You could end up getting a constant, right? In the original SPOO paper written by Adam, Adam, he's also a faculty in Columbia, they derived kind of an upper bound, a smooth upper bound to the regret function here. But in our particular case, it turns out we use another approach called the perturbate loss function. Turns out to be work better in our particular arbitrage case. And the idea is also very straightforward, is we introduce a Gaussian noise to our predicted prices and take the expectation of it, which ended up with a smooth function, right? So here, this is also illustration from that original perturbate loss function paper, that if you think about, again, here in with the arbitrage, we have a linear objective function. A linear optimization is a polyhedron, right? So if you think about this, is basically an optimization function. So by the simplest algorithm, the solution to a linear problem will always land at one of the vertex, right? But here, right, if you look at our problem, our prediction from our price prediction from our prediction layer ended up being a parameter in our linear optimization. So here we are basically varying our model parameter or the objective cost, the cost of the objective function in our linear programming, while our feasibility region, right, the linear constraints stay the same. So in that case, we will end up with a kind of more like a discrete change, right? Because our solution will either be in one vertex or the other, right? We will never be anywhere in between, okay, as seen in the simplest algorithm, right? So what we ended up doing here is by introducing a noise and then expectation, we can kind of smooth out the original linear problem. So eventually give us a smoother change of our decision P with respect to the change in the cost of the objective function, right? So most of the work in this paper is we show that the perturbated loss function in the storage case is a convex and also Lipschitz continuous layer. That means it has, of course, the learning problem itself is still non-convex, but at least it shows that layer, this decision-focused layer we introduce does not causing, is easy to compute and does not jeopardize the full training process, right? And also, this is also very easy to implement in practice, just with Monte Carlo sampling of the noise and taking the average, aka the expectation. Okay, so this work was mostly carried out by Ming and Saud. So here they implement this method and compare with a RSTM network versus a feed-forward multi-layer perception neural networks, right? So one thing it shows that if you compare the final profit, the decision-focused learning method performance is better compared to the other method if the efficiency is less. So the other way to think about this in cases when the physical model or the battery model is more constraining, the decision-focused learning method will bring us more benefit. Okay, it also shows that if you compare our decision-focused learning method versus the feed-forward neural network and RSTM neural network, the RSTM actually has the worst performance, given that it actually always overly smooths the trend. Okay, and if you zoom in on the price prediction, is more obvious that if you look at a general prediction trend, the RSTM, the red line, actually works the best. Well, our orange line, overall the match is not the best, but we do show that we can capture kind of the occurrence or the timing of a spike and a value, and that's what storage really need, right? It's need the timing of the spike and the values. Okay, so yeah, and that's kind of the key idea of this decision-focused learning framework. Okay, so based on this, I want to finally talk about how do we generate storage bit using the prediction, or in other scenario, maybe based on the price distribution, right? So based on the FERC Order 841 in published 2018, it requires all the system operators to allow storage to offer into the electricity market. So now storage can submit both sell and buy bits in the energy market, right? And in real-time market, the storage must use base to indirectly manage the state of charge. This is this is an illustration from one of the earliest paper in this perspective, in this area, from Warren Powell Princeton group, that shows you have the sell bit and the buy bit, and this will be the kind of the price, kind of example price trajectory. So the battery will charge if the price falls below the buy bit, or discharge if the price goes above the sell bit, and do nothing if any somewhere in between. Okay. So so in that work, Warren was using approximate dynamic programming to generate the bit, but here we show that we can actually solve this problem using a much more simplified approach, but also based on just based on dynamic programming, right? So if you recall that our deterministic version of our objective function is a linear equation here, and then we can come up with a equivalent recursively defined dynamic programming reformulation with, and the key here is we have the value to go function, right? And the value to go function is a function of the state. And here we only have one state, which is the state of charge, right? So you see here, right, every time period, we are maximizing our immediate loss or gain plus the future value of the storage, right? And the future value storage is defined recursively as the maximized value of the next time period, right? And of course, you do this backwards, you get all the value functions, right? So what does this has to do with bidding, Okay, so you look at it, this function, right? This is basically our immediate gain from the market, right? This is the price times difference between discharge and charge. And here, this basically represents our cost. And this, we have two components. The C represents the physical discharge cost, which could be degradation, and the V represents our opportunity cost, right? So here we can separate this is the cost function, and based on this, we can define our offer curve based on the marginal cost function. So we're basically taking a partial derivative of this with respect to discharge or charge, and that gave us a very neat function of marginal, you can see this marginal cost of discharge, marginal cost of charge, and they are the function of SOC, okay? So, and then the next question is, then how do we calculate this value function? This was actually one of the major work I did back when I was a postdoc at MIT. It shows that there's actually a pretty neat way that you can calculate this value function. Of course, the detail of how we arrive with this equation is kind of complicated, but this was mainly derived based on Dou decomposition, based on the KK decomposition. But we can derive this function that can almost analytically update the value function based on the piecewise linearization approach, okay? So if you look at this, the marginal value function over the next time period, over the previous time period, is a function of the current value function, while p, eta, lambda are all parameters that are known, okay? So we can calculate this very fast with one backwards recursive calculation. So based on this, of course, before I look back to Baiting, we actually used this to wrote a few papers on solving a different version of stochastic dynamic programming. Because if you think about this, although this is deterministic, but if you combine this with, if we model the price of electricity has a Markov process, right? And so each price node is a discrete price node. We can immediately apply this approach, and we show that using this approach, we can very quickly solve stochastic dynamic programming for energy storage arbitrage. With in Euroton market, we have a 5-minute resolution, right? So in 1 year, we have around 100K time steps. And they show that using this approach, we can solve like a 1-year SDP in just 100 seconds. And we can show that we can get around 70% theoretical profit in the New York State data. And also we, of course, the detail is more in that paper, but modeling stage dependency, that the price of the next time period depends on the price realization in the previous time period. And also modeling the dependency of day-ahead real-time price versus the day-ahead price, right? So real-time price distribution also depends on day-ahead price. Each will give us a kind of a 10% improvement of the profit, right? The other work we did kind of along this area is we further show that we can incorporate more complex battery dynamics into this framework. That this is particularly more common in electric vehicle cases where the battery or the BMS is more constraining. So if you have a EV that there is this CCCV, constant current, constant voltage charging profile, that will end up giving you a power versus SOC profile that looks something like this. Okay, and also we have efficiency, discharging power rating at a cycle penalty. So everything's become a function, or more specifically, empirical function of state of charge. If you formalize this, we can update our model. Of course, now is nonlinear and pretty much non-convex, but it just in this paper, we never really try to prove this is non-convex. But these are becoming a nonlinear problem in which efficiency, power rating, and cost of discharge all become empirical function of the state of charge. And then Georgia, which the student who did this, did spend quite a lot of time and actually showed that the analytical value function update method that we came up with also applies to the nonlinear battery characteristic. Of course, now you see there's a lot of partial derivative here, but we show that it actually still maintains the very competitive computation performance while remaining accurate compared to a mixed integer linear programming benchmark, right? So, but apart from this, what's mostly important is, again, going back to the value function. It showed us a very neat way to come up with battery charge and discharge bit based on price prediction, right? So here, if I came up, if we go back to that price profile had before, we can generate the optimal or hindsight optimal discharge and the charge bit. You can see this case, we basically show that the battery discharges, right, when the price is low, and then, right, we call that the battery will discharge if the price is below the charge bit, and then discharge when the price ended up higher than the discharge threshold, okay? So not only this, we also recall that this is actually the bit is a function of the state of charge. So we also saw that these are actually the actual storage bit should be dependent on the SOC that kind of gave us a range of a charge and discharge bit. And this is actually one of the idea if you think about improving future market design for energy storage. This is one of the initiative that we wrote a proposal back in 2000. Wrote a paper back in 2023 with Gabe Murtaugh at that time was working in California, and also Di Wu from PNL, showing that if you think about a battery market model, it's really the bit should be depending on the state of charge instead of the power, which is our the power bit are really designed for conventional generators, right? And also another thing we are working on this is industry implementation. So we do have a collaborator in Concord Energy in Texas that what they are really doing is doing power purchase agreement for data centers in Texas, and one of the major portfolio in their method is derived battery bits. It's bidding batteries in the electricity market, and actually the main reason they do is to hedge against their risk in long-term forward contracts. So we've been working for them for over 2 years now. So in this summer, we finally implemented our price prediction and a bit generation algorithm onto their cloud platform. So now this algorithm is running in real time. It's not really controlling every physical battery asset for now, but all the data input to this algorithm is in real time from the data provider. So we do show that in one day, this is which day? July 1st this year, we show that our algorithm successfully captured most of the price spike in ERCOT, except the last one. So we kind of missed the last one, but all the previous price spike, our algorithm captured them. So our sponsor was really happy with this result and can agree to continue to fund us. And then next, we were going to do multi-service co-optimization of battery with other services. And also our sponsor. So this is not my group, but our sponsor's company in Austin, Texas is hiring data analytics and algorithms. If you're interested in working this project, I can definitely connect you to the company. All right, so that's kind of the work. We kind of some of the work we did in this area, and really the key conclusion here is existing market design is suboptimal for storage. And the main reason is there's still, especially in the real-time market, battery cannot participate in this market by simply submitting their physical parameter, right? They have to be speculative players, right? But it works. With competition, it's still work towards efficiency, right? And understanding the opportunity value function is critical in developing market solution for energy storage. I think the industry also came to realize this. If you look at some of the recent initiative from California ISO and also ERCOT, which is the Texas system operator, they are both emphasizing the importance of state of charge regulation and management in their newer market initiative and models. And also the storage operator also came to realize that when they design their bidding strategy, they really need to think about what the role of SOC, state of charge, play in this. And also distributed battery that may be overcredit constrained need to be incorporated into trade-off control trading solutions. So sometimes, depending on the battery, we need to think about how to address some unique battery characteristic into the market offering. And also machine learning approach is essential, but must incorporate some think about how battery would actually behave, right? The price spike, the price extremeness, and other physical characteristic. Okay. Yeah, so want to give acknowledge my group. So most of the students I mentioned graduated, but there's still me and the South here. We have, of course, a whole other cohort of students working on other topics. Some of them will show up in the Informs meeting next week. So if you're there, also feel free to remember to check us out. And also our collaborators from Columbia Business School, P&L, and also Gabe. I believe he recently left KAISO, but yeah. And also founding agencies, especially the Concord Energy, who have been supporting us in that industry project. Right, so yeah, feel free to check my website for detail, and I'm happy to answer any questions.
Very nice talk. I want to ask something, and I just can't. I'm not sure if you covered this or not, but in modeling in your battery model, are you accounting for the power lost when the battery is charged and discharged? So there's an impedance in the battery, so that when you charge and discharge it, you lose some energy.
Yes, that's so on the condition that we want to maintain a linear model, the way we do it is to use eta, which is kind of efficiency. So,
okay, so it's a static efficiency.
Yeah. This will typically, for linear model, this will be somewhere around 0.9 to 0.95. But in this case, we can actually also model it as a function of state of charge. So in this case, you have achieved the highest efficiency. We are close to 0.5. Well, the efficiency, here you may have higher impedance, here maybe higher voltage. That can the efficiency goes less. But in this case, we kind of will, in terms of optimization, if we introduce this, that kind of give us a bit of a non-convexity or non-linearity in the model there.
Thanks.
Yeah. Thank you, Bob. Very interesting talk. I have a question about the decision focus part. So I saw that the optimized forecast that maximizes the profit appears to be the most conservative for the prices. It's consistently underpredict the price more than any other.
Yeah.
Does it mean that this optimal forecast discourage storage to participate in the market? Does it depreciate the price so much?
Yeah.
If you say an operational problem, maybe not in the long term, right? It would basically indicate that there is not much of a difference to arbitrage amount and
it's a good point. We did look into this, but in fact, that what we do notice is in decision focused learning, if you're only using the decision focused loss function, basically meaning the training will only looking at how battery behave to the price prediction. It will not look at the price prediction itself. right? So if you think about, we may have two very different prices, but the battery ended up doing the exactly same charging and discharging pattern with these two. Another decision focused learning will feel that's very good. Okay. We do have a kind of modification in our method that we can add another norm2 loss function. So that means that also, let's try to be close to the actual price. But that is one thing with decision focused learning is actually the prediction will look a bit awkward, weird. In this case, yeah.
Thanks for your talk, and I'm curious if your findings can be generalized to longer durations and storage. Like mostly you are talking about battery, but what if it's like hydro or storage because it's multi-day balancing? And my second question is that from your understanding, is it easy to incorporate this kind of strategic participation of battery storage into capacity expansion model?
So long duration storage, especially if you think about the pump storage hydro, they're not new, right? There has been much longer in the power system than batteries, but before I believe at least in the US, most of them they're self-scheduled. Okay. But yeah, we are introducing some new concept for long duration storage. And there is some very interesting discussion along this line, particularly based on how much future you to predict. The US market or most electricity market works on a daily basis, right? If you think about the battery with 2 to 4 hour duration, they are basically looking at 1 cycle per day. So you need 1 day of prediction, right? However, if you have like a weekly storage, right, that is supposed to do weekly cycle or monthly cycle, then ideally to do weekly price prediction or monthly price prediction. And that things get significantly more complicated, especially we don't have a weekly market. So that's kind of, I think that was a challenge discussed by some of the market people saying, should we introduce like a multi-day market just to clear that? But on the other hand, we are doing some work in this that actually in this front, and that actually shows it's more beneficial to use this approach. That instead of if you think about having weak storage, right? I want to schedule this weak storage. One way using MPCS, you need to predict 1 week of electricity price and schedule battery. But instead, using this method, you only need to think about what's the opportunity value of that storage at the end of time horizon, right? So in that case, some of the work, not including here, we do show that this kind of a dynamic programming framework, this is actually, not that different from reinforcement learning. If you think it's mostly about how do we come up with a value function, do perform better if you have a longer duration battery. Compared to NPC. So Johan.
I actually have a question about this formulation I was going to ask you. So the last constraint here, just set P equals 0 if the price goes negative, seems like important mathematically just to keep the problem nicer so you don't have to decide what discharge and discharge constraint. But like you want the battery to discharge if the price goes negative because that helps balance the power grid. So you're sort of like artificially reducing that effect for computational reasons. Is that the way to think about it?
Exactly. So what do we do now? So in most of the scenario, it's a kind of a neat trick, especially if you publish paper in this domain. The reviewer always asks you, what if your battery charge and discharge at the same time? And this is the way that to get rid of it while keep from convex. But we do observe our algorithm performance deteriorates in cases when we have a lot of negative prices.
And the market deteriorates. I mean, the efficiency of the market deteriorates because you're not using the battery to discharge what it needs to. It needs to most even, I think.
Well, I would say when price is negative, that usually means we have more power than we need in the grid. we have excessive renewables, so if the battery discharge, it kind of worsens the excessive energy. So in most of cases, when there are only occasional negative prices, our algorithm doing fine, but we do.
If the price goes negative, it's gonna consume as much power as possible and be paid to do it.
Yeah.
Good.
Yeah. No, P is the discharge. B is the charge.
I see.
Yeah. P is the discharge.
Okay.
Yeah. But we do notice in one area, which is the north region in New York, that's kind of the border to Canada. That one has very negative prices due to the congestion. They have a hydrocarbon, and then they have a lot of wind generation. So in those cases, when there are persistent negative prices, our algorithm, and I would say in that case is probably in hindsight, you should have discharged. The price is so negative that you can even arbitrage negative prices. You can charge with prices minus 150 and the discharge with prices minus 50. And in that case, our algorithm doesn't work very well, but that's a pretty extreme case. Yeah, but it does happen in up north in New York. Yeah.
There one more question?
Thank you. Thank you for the interesting talk. So I totally agree with the fact how you incorporate the battery degradation because it's very SOC dependent.
Yeah.
I'm just wondering whether you consider calendar aging when you model the battery degradation.
Okay. A good point. In this case, no, because we are looking at the daily operation. So in this particular setting, calendar degradation will be more considered as a kind of a sunken cost. But we wrote another paper, also using dynamic programming, but not to optimize daily operation, but to derive the opportunity value of the battery capacity. So in that case, it's a dynamic programming over 10 years. In that case, calendar degradation will show up. Equivalently, if you really want to model, of course, in that case, you have another state, which is the capacity of the battery, but then calendar degradation will show up as a constant term that reduces reduces this guy day by day. Yeah. So that is same. Yeah. Okay.
For time.
Okay.
Thank you very much.
Yeah. Thank you. Thank you.
It's we can.
Yeah. Yeah. Oh.
No, it's there. Oh, I'm just trying to. Really funny.
That's
Yeah.
Oh, I'm sorry. I'm okay. Yeah. So.
Hi, I saw you. Sorry. Yeah, I saw you have all kinds of questions.
I guess I have one about like the student focused learning part. We've been trying something.
But outside of the class.
Different applications, but why are you? I was wondering why you're using like the regret optimization. I was like what makes the regret optimization better for this application?
The regret optimization is mostly to derive their. Yeah, if you just build a CFL, you don't need that. You just need you can just use that objective function in your training. But it's really just to acknowledge the spoof framework. They have the regret, and they ended up deriving a upper smooth bound of that regret function.
Because you have the sum with the smoothness of delta.
Yeah.
You have that problem because it's like feasible space going the same.
Yeah.
But so you always land at one of those solutions.
Yeah.
You don't get the optimization.
Yeah.
That's why you don't.
Yeah. That's the fundamental problem that people have various ways. We use the derivation method, the school paper actually they were proposing upper bound, upper approximation. So I'm pretty sure there are other people trying other methods. It's mostly depending on actual performance, like which ones, theoretically they all work. It just which one works best in practice, and in our case, it's the perturbation one. that works best.
Okay, okay, makes sense.
Yeah.
Thanks.
You're not supposed to know that yet.
Yeah.
Thank you for.
very similar.
I'm wondering, because you talked about your data is based on
Sure.
SOC, right?
Mhm.
I'm wondering how do you get that current?
Oh, that's from some literature. There's some lab experiment.
Yeah, because I'm like working on similar things about storage,
Mhm.
but I found that it's very difficult to model the losses.
It just, when somebody.
Because I found very, like, some literature, they model this efficiency in a very complicated way.
Yeah, there are
In the least.
a lot of paper with data. I think the one way they do is measure the impedance
Seemed pretty good.
and then calculate what's the theoretical.
So,
Yeah. Because if you think, if you only cycle the battery, it's actually not trivial to measure it, right? You
Yeah.
cannot cycle the battery in every small piece SOC, but they are mainly doing it by impedance measurement.
I see. Also, basically, when you have different